And the recording began. Terrific. Thank you, Erin. So our speaker today is Sabetta Matsumoto, who is an assistant professor in the School of Physics at Georgia Tech. Her research group, the Matsumoto group, works along the intersection of geometry and material science and includes like a theme that sort of studies how local structure influences global geometry. And this has amazing applications. I've loved every talk that I've seen Sabetta give, including, applications to programmable matter that can be 3D printed and change shape, or studies of the topologies of fabrics. And so I'm really excited to hear from her today. So I will I will pass the mic over to you figuratively, and yeah, let's introduce let's welcome Sabetta.
Thanks so much. Let me see if I can get my screen share going. All right, can you all see my screen? Awesome. All right, thank you so much for the invitation. I'm gonna maybe have a kind of slightly different style talk than like we often get here, because we're gonna talk a little bit about how trying to understand knitting from like a mathematical point of view, like, and thinking about illustrations and things like that led to a proof that I guess I guess I can sort of state the theorem, which would be that all two periodic knittable structures form ribbon knots. So we'll kind of unpack that over the course of the next, 35 minutes or so. I guess the other thing is, since this is maybe a little bit on the technical side, just like interrupt me if you have questions, or put your questions in the chat and Erin or Gabe will interrupt me. So I don't want to like go totally off into the weeds if people aren't following along. So I guess I've been knitting forever. I learned to knit with my mom when I was little. And I did it as a hobby, like through grad school and postdoc. And then I got my own research group and I was like, hey, let's study it. And then the downside of taking something that's your hobby and turning it into your research is you no longer have any hobbies, and like your whole life turns into a research project. So that's kind of what happened with me in knitting. So the piece you see here, this is called The Dragon of Happiness. And the pattern is by a woman called Sharon Winsauer. And I'll get to it a little bit later, but like, this is definitely one of the things that like inspired me to go down this research trajectory. So before I get into too much stuff, I want to show off my amazing research group. And our collaborators. And today's story, I guess the heroes of it are Shashank Marconde, Miriam Coosbury, and Sarah Pritchard. And so Shashank was a grad student with me who has now graduated and gone on to bigger and better things involving, making money and being able to stay in the US, which is a very awesome thing, because it's not very easy to go through the US academic system with visas. I'm sure many of you know that. Yes, Miriam, was a postdoc, an NSF postdoc at Georgia Tech, and she's recently accepted a position at Amherst College. So yay, congratulations to her. And Sarah was an undergrad who was working with us, who's just graduated and is starting her PhD at Duke. So these are all amazing people, and they'll be the ones who are responsible for the work I'll tell you about. So I guess our lab, we like to say knitting is coding, and that's maybe kind of a strange statement to make in some senses. I mean, there is a sense in which there's a code. Every little character over here corresponds to like a topological manipulation of yarn over here. Not quite unique, but most of them are different, or topologically distinct anyway. But I guess the thing about this, I guess this particular piece that was really inspiring to me is that I guess I'd been knitting for a long time when I made this pattern, and it's obviously really really gorgeous, but it's also quite intricate. And a lot of lace knits take advantage of the same few different types of stitches, just like recombined in lots and lots of different ways. And so I was sort of expecting that when I got to making this piece, except there were these different stitches. So there's some here that have like equals signs. They're like above these, like there's like a dot and an equal sign above it. And they're in this sort of flames coming out of the dragon's head and also on its beard. And that was a stitch that I totally had never seen before. And it really surprised me because I was like, oh, well, I've been knitting forever. I understand knitting really well, but like, what is this? Like, this is new. I thought everything was combinations of stuff I already knew, but like, what's going on with this? And so that sort of set us down the path of trying to understand this mathematically, and trying to ask the question, what even can be knit? And I guess the other thing about thinking about textiles as coding is that this isn't new. This is a picture of a jacquard loom over here, and this is a thing that you do for weaving. And so in general, when you weave, you have a pattern of you have warp threads like this, and then you take weft threads and sort of go over, under, over, under, over, and so on. And so this pattern right here is a plain weave. But what happens when you use a jacquard loom that's different than regular looms is that you can take any of these sort of crossing intersections and decide whether you want an overstitch or an understitch. I guess they wouldn't be stitches because it's not knitting, but any of these crossings you can like individually address. And so this is what the jacquard loom does, and it uses these punch cards over here to determine that. So this is a thing that is it's one of the earliest forms of sort of binary computation that existed. So it's still used today. So this is a textile that's being made with a modern jacquard loom. It no longer uses punch cards. It's all computerized, but what it does and how it interacts with the fabric is effectively the same. So knitting has this property that it has lots of different stitch types, but it's not binary anymore. It has like all sorts of different, I guess, letters, and they can be rearranged in lots of different ways. The other thing about knitting that's a bit strange is that letters are not necessarily one grid space by one grid space. You can have letters that are different sized rectangles. So over here, down here, you can see that there's some of these patterns that run across like 3 or 4 grid boxes. And so knitting has a more complicated structure as like a context-free grammar compared with other textiles. So I'll tell you a little bit about how we unpacked what knitting was. So first we'll show you what knitting is, or how to knit. So the knit stitch, we've got, I'm gonna show you what my hands are doing up here, and then a planar knot theory diagram down here. And so you can think of the needles as punctures in the plane. So here, both needles are pointing into the plane right now. So what I've done is my needles have a whole bunch of loops on them. I have loops on my left needle and loops on my right needle. And so what I've done is I've taken my right needle and stuck it through the last loop on my left needle up here. And so that's the first thing in taking a stitch. Then what I'm going to do is I'm going to wrap this free yarn here around my right needle. So that's this loop here. And then what I'm going to do is pull the right needle through the loop on the left needle. So that's what I've done here. This is the first sort of stitch I've made. And then to complete the process, what I'm going to do is drop the stitch off of my left needle. And so now I've made a new stitch and I've passed it through to my left needle. So basically I'm just taking loops and pulling them through loops. And that's the whole process of knitting. So far, so topologically uninteresting. It's it's a bunch of slip knots. It's the old school, I don't know, there was some like Weezer song when you like pull the thread to unravel your sweater. And yeah, so it's not really interesting from a knot theory point of view. So we kind of wanted to make it a little bit more formal from that side. And so we can do that by looking at what happens when you go from a stitch to a textile. And so this is, I guess this is the unit cell fundamental domain of a knitted stitch. And then what textiles do is textiles apply this periodically. So basically you have a set of stitches that go across and they repeat. So we can now think of textiles in terms of, well, I'll show you a little bit more, but in terms of sort of more of a closed periodic unit when we can sort of take the quotient of it. So there's a couple of different types of stitches. There's the knit stitch is the stitch I told you about before, and then there's a purl stitch. And the purl stitch is exactly what happens if you take a knit stitch and turn it upside down, like rotate it and look at the back of it. So they're really the same stitch, just viewed from opposite sides of the fabric. And depending on how you put these together, you can get really different fabrics with different mechanical properties. And so this is what the other half of my lab does, is study the mechanics of these and sort of how to assemble them into cool structures. So this is the what's called stockinette fabric, also called jersey if you're a machine knitter. And this is the back of it. So this fabric has distinct front and back, and the back of it would be called reverse stockinette. And so this is like actually a pretty stiff fabric. You can also see that it's curling up. It wants to have negative Gaussian curvature. So I combine them in different ways, these knits and purls. I get different fabrics. So the first one is garter stitch. So this is alternating, these are alternating rows of knit and purl. And that's this fabric. So this is very stretchy in this direction, a lot stretchier than stockinette in this direction. And you'll notice it's also flat. It's sort of symmetric front to back. And I just want to point out that every single one of these swatches I'm showing you has the same number of stitches across and rows up and down. The next one we have is ribbing. So this is alternating columns of knits and purls. And it's really stretchy this way. It's about an order of magnitude stretchier than stockinette in this direction. And then it's not much stretchier than stockinette in this direction. They're pretty equivalent. And then lastly, we have seed, which is a checkerboard lattice of knits and purls. And this one is, it's pretty similar to garter stitch in a lot of ways. This particular one is about equivalently stretchy, but there's a little bit more variation in how this one turns out than some of the others. So, so that's sort of what the other half of my lab does. And we can try to understand these fabrics. So what I showed you for these is these are a fundamental translational unit for each of these fabric types. So we can take those and look at different ways of sort of quotienting out by that the sort of periodicity of that, and trying to create a compact manifold in which we can study our knits. And so one thing that's a little bit problematic for these is that if I were to take a fundamental translational domain that looks like this, and I identify opposite edges with each other, and then look at the knot that's formed from the knitted textile, and then I did that with something that's different over here, I'd get different knots with different topological invariants. And that's not really useful. The whole thing about topological invariance is that the same structure should produce the same invariant. So there's a way of overcoming this, and I'll get back to that a little bit later. And so this group, Grishinov, Meshkov, and Vasilyev, were able to look at certain polynomial invariants and show that they can, in fact, identify all of these textiles with one another that way. So our knots, we like to think of in what we call it the thickened torus, which is basically, if you take a donut and you look at the glaze on it, a space of all two periodic textiles lives in the glaze on the surface of a donut. And we can construct a manifold like this quite easily. We can take S3, or you can sort of imagine R3 and taking the entirety of space and then removing a little bit of space, like a little bit of space along the red curve and a little bit of space along the green curve. And everything that's left over will have the topology of a thickened torus. So we're going to take advantage of basically adding in an auxiliary link to make studying all of our knots easier, because now we can study them in S3, which is where most knot theory software and things like that live, or at least work best. And so this is what we do. So here's our fundamental translational unit, and now I've put it in the thickened torus. And now what I want to do is glue this together. So the green side is attached to the green side, the red side is attached to the red side, and then instead of 4 edges along here, these will all be identified as a single edge. So how do I do that? So what I'm going to do is I'm going to put it in. So now you can see the hop link, the pair of auxiliary links that I took out, and I need the green sides to wrap around this green boundary region. So I can do that like this, and now I've identified both green sides. I'm going to do the same with the red. It's a little bit harder, so I have to like pull them up out of the plane like this, and then they're going to wrap around the red link component like this. And so this is now my knitted textile, or my knit knot that is now an actual closed loop, and it is it's in S3, and it has basically some auxiliary gadget around here to make the calculations easier. But basically all we do is like look at what's in this dashed line and sort of put new things in, or pull things out of there and try to see what is knittable. And so we are going to call the thing that's in here a precursor to a link in S3. So we're mostly going to be dealing with things inside this box. And we'll just have to keep in mind that there's some other stuff around it in S3, or we'll deal with it especially as I explain. So what can be knit? So I guess we were working on this project, I guess, a while before the pandemic. This is Shashank Markande and I were doing this, and so basically he hadn't knit before he joined my lab, and then he learned to knit. And what he was doing was taking, I gave him a bunch of stitch dictionaries, and he was just looking through them to see if he could find anything in common between those stitches. And if he puts them, if this is that sort of dashed box I showed you before, if he puts them in with that sort of gadget around it, are there any patterns that he can detect? Is there anything in common that all of the stitches form sort of topologically? And he's playing around with this. And he had noticed that all of the knittable stitches that he saw in the dictionaries had this property that they're ribbon. And I guess I'll give you the sort of colloquial definition of ribbon. Basically is, if you imagine that your knot is the boundary of a disc, the disc can only pass through itself completely. It can't pass through itself in sort of like an X shape like this. So that's, I can show you different definitions later, but that's basically what you want to think about. And so Shashank was playing around with this and was like, okay, well, are there other things that are ribbon that maybe can't be knitted, or where does this sort of, this boundary of things being ribbon, like what does that have to do with knitting? And so he was playing around and was like, well, what about this structure? Is this something we can knit? And I was like, well, let's find out. So on Monday, bring some needles and yarn to the group, and we'll play around with it and see. And so he did, and this is the result. So there's 6 of these stitches here. There's this 2, 3, 4, 5, 6. And so Shashank, who had never knit before coming to grad school, was working on this knitting project, and just from math invented a new knitting stitch, just because he noticed that there's this property that all of these knitted stitches are ribbon. And he calls it the cow hitch stitch because it's reminiscent of a cow hitch knot. And I don't know, I think that's really amazing that he was able to like link this sort of pattern together, and then it turned this into a conjecture that all knittable stitches must be ribbon knots, and then we've turned that conjecture into a theorem. And it's also raised the question of the converse of, are all ribbon knots knittable? And we can show counterexamples to this, so that the converse is not true.
Can I ask you a question from the Q&A that was posted?
Sure, please.
It was asked, what exactly is a ribbon knot, and how do you maybe precisely define knittable?
Yeah, so we're definitely gonna get there. So knittable is a knittable. Yeah, so I think the next, both ribbon knot and knittable have formal definitions coming up in just a little bit. So I guess, so knittable, let me just skip ahead to knittable, because that's a much more complicated question than I guess ribbon knot has like a sort of technical definition in R4, and I have that a little bit later, but knittable is actually like the really interesting question, and this is what we wanted to understand. So we did this by sort of trying to take apart what happens when you knit. So when you knit, you have loops on your needles, and you sort of make slip knots through them, passing them back and forth to each other. So first thing you have to do is get loops on your needle. And so knitting people, we'd call this a cast on. And for our definition here, I'm going to make this an component unlink. And this is what we're going to call an unknit. And then the next thing we want to define, so the other definition we have is what we're going to call a trivial row. And so these were defining on an annulus, by the way, just to make life a little bit easier later on. So what we have is a trivial row consists of a single loop in the annulus direction, and this is the working yarn, and then an end component unlink, which is the stitches that are going to be put on the next needle. And so the process of knitting are just going to be using planar isotopies of the yarn. I'll do everything as if it's a planar diagram. So we have all of the Rittmeister moves. We have these are sort of the 3 moves that we are allowed to make, and we'll take advantage of those. The other thing we're going to be using is called band surgery. And so band surgery, what you do is you identify a quadrilateral where opposite edges are on parts of your knot, and the other two edges are not on your knot. And then band surgery swaps which edge is which. So after band surgery, the bit that was your knot now becomes nothing, and then the bit that wasn't your knot becomes part of your knot. So we're going to take advantage of these two moves to construct all of our knits. So if we wanted to make a knit, we're going to start with some unknit. So we'll start with an end component unknit down here. So this is our cast on row. And then we have, I guess, our working yarn here, and our goal is to have the working yarn interact with the loops that are already on our needles, and then via band surgery, we're going to connect them to the loops that are on our next needle. So here's a bunch of ambient isotopies with the working yarn. And then next I can do band surgery on these to basically glue them onto the new needle. And then the whole thing is basically rinse and repeat. So if we have another row, we have a new set of working yarn, and we need to connect this to a different number of stitches on the next needle. And so we can do this with some set of ambient isotopies and then with band surgery. And so basically, we can do this as much as we want, but if we want to get to the two periodic structure, we need to close this up and make this on a torus rather than an annulus. So we do that by basically, we've taken our annulus and stuck it inside a torus, and then I want to glue the top to the bottom. And I want to do this again using band surgery to actually make it two periodic. So I'm going to now identify each of the loops up here with bits of my cast on, and then I'm going to glue those together. So this is pretty similar knitting wise to what you do if you graft things together for the knitters in the audience. I guess without the surgery part, but you are using a needle to do kind of a sewing weaving bit when you do that. And that will make these things properly periodic. So the other question, let me answer the other bit of the question that was asked about what is the definition of ribbon. So basically this is the technical definition. So K is our knot, and this is going to be in S3, and S3 is going to be the boundary of a 4-ball. And then we're going to take a disc in that 4-ball whose boundary is the knot. And so that's what this sort of illustration is here, is showing I guess this would be the knot, and then there's a disc in R4 with the knot as its boundary. And then basically you put a Morse function or sort of like a height map on that disc, and you can kind of move it around up to isotopy. And to be ribbon, you cannot have any interior local maxima. So you could not have this bit up here. That there's this is I guess, what's called a slice diagram. So knots that are slice are allowed to have these local maxima, but if it's ribbon, it's restricted to have none of those. And basically, I'll show a little animation of what it's like to go like through the levels, like looking at sort of a video where we have where we're like moving through the fourth dimension, basically. And so this is a ribbon knot over here. And so this is a picture of it where this is, I guess, the sort of boundary of the 4-ball, and then we're going to move into the 4-ball. And we get to our first saddle point, and that saddle point is going to be right here. And so this is a little bit thickened because we want to be able to actually see the saddle point. And so what the saddle point here does is it basically breaks the knot open right here. And now we can use sort of ambient isotopy to sort of retract these sort of bits of knot. And that's what happens as you go further into the 4-ball, and you're left with these little bits over here, which are ambient isotopic to 2 disks. And then these are the 2 local minima that you would find. But we've only seen local minima and saddle points as we do this sort of sweep through R4. And so what the process of knitting does basically is we sort of run this whole process, but in the opposite direction. We start with all of these local minima here, and then we, via ambient isotopy, wrap them around. And then the last step is to basically connect them all up. And that's the sort of step that we're using band surgery for. So that's so basically we can construct oops, what has gone on here? So basically we can construct all of our knit stitches so that they by definition have to be ribbon. And there's a potential little additional step where we have to make sure that everything is properly in S3, because I've done everything on the glaze on the surface of the donut space, the thickened torus. So I need to do one last step, which is Dane filling that in. So I'm filling in the 2 solid tori that I've removed. And so once we do that, we can guarantee that everything is ribbon. Because the last thing we want to do that we don't really know how to do yet, so this is kind of in progress, is figure out how to sort of glue stitches together to make more complicated structures. And so we call this annulus surgery. So everything lives in these thickened tori, but we have to cut them open along an annulus, take another thickened torus we've cut open along an annulus, and then glue them together. And so this is what it would look like in a planar diagram point of view. We can do it vertically. This turns out to be more complicated, but this is sort of a goal of what we want to do. And then once we have done that, we can come up with basically this is sort of a language for looking at all of the sort of possible permutations of different types of stitches to make a 3x2 unit. So we don't actually know how to do this set of enumeration. It seems like it's actually really hard computer science problem. So that's definitely an open question. And if anyone has suggestions for it, please do let me know. And so I guess with that, I will thank you all. This is a QR code that goes to our lab website. It should actually work. So I guess I'd be happy to take any questions.
Great, yeah, thanks so much. If anybody has questions, feel free to post them in the Q&A, or I think if you raise your hand too, I can temporarily unmute you. We do have a few moments for questions. It's a lovely talk. So I'll post this lovely talk in the Discord. I do have one question. Am I understanding that this sort of band replacement sort of like always shows up as a saddle point in the Morse theory? Is that sort of what you're showing? That's so interesting.
Yeah,
And so then
that's
it's like the global geometry of that manifold, because you can't actually ever get any other sort of local maxima there. Like, do you get some invariant there?
I mean, up to isotopy, there's
Yeah.
local maxima.
So a post in the Discord asks, or no theory Pat asks, what is an example of an unribbon knot? Is that it?
Oh, I mean, I think like a trefoil or a knot like that wouldn't be ribbon. So most, I guess, I wouldn't say most knots aren't ribbon, but it's a sort of special subset of knots that are ribbon. And I think if we were to contrast knitting with weaving would, I think, virtually always produce knots that are not ribbon. So those would be more like things like trefoils and things like that.
So this proves that the trefoil is not knittable.
Yeah, the trefoil as a knot wouldn't be something that you could knit. I mean, you can, I guess you can crochet a trefoil, but as like that knit path, that's not something that's sort of knittable by standard, like needles and knitting constraints. You'd have to have an end to thread through something, and that sort of violates what knitting is compared to weaving.
Are there any other questions? I'm also monitoring the Discord if folks post there. If not, feel free to continue chatting on the Discord threads in the seminar page for each of our 3 talks today. I saw that Erin posted a few things in the chat. So I just wanted to say thank you so much to all our speakers. And Erin, would you like to close us out?
Yeah, thanks. Thanks to all the speakers for a lovely presentation today. That was super fun. And yeah, I just posted a few things in the chat just to remind you once again, there's the Discord invitation. There's also the Google form for you to sign up to give a show and ask presentation. I hope you do. The longer talks are recorded unless the speaker doesn't want them to be, but so far all of our speakers have consented to that, and we've started a YouTube channel, so the YouTube channel is also there in the chat. And finally, I just posted the Illustrating Math general website, which includes information not just about the seminar, but other things going on in the community. So, so that's what I wanted to say. And any further conversation, I think we should move over to the Discord at this point, and I will stop the recording. Thank you all for coming, and see you next month.
Bye.